Okay, so all it remains is for us to deal with the remaining three scenarios. So let's say a company is going to make two production processes, and that's going to fulfill a demand for two products. But the company should do that only if it accepts an order. So what does that mean? It means that now the company needs to make a decision about Z, which may be 0 or 1. If Z is 1, that somehow means the company is going to accept an order, and that's going to earn him $50. So that's one thing, but once you accept this order, you must make some products to fulfill the demand. And the demand is here, 6 and 8 for products 1 and products 2. So you need to somehow determine the amount of hours to run your production runs, to production processes, and then that's going to have some consumptions, and eventually that's going to tell you that you need to pay some cost about this. So you're going to see that if you don't accept this order, saying that if you put Z equals 0, then somehow you still need to make the production planning, but you don't need to execute it. So that means you don't need to pay any cost actually, as long as you don't accept this order. Okay? So there must be some way for us to linearize this particular formulation. Here, when you take a look at this formulation, the nonlinearity appears at the maximization objective function. We somehow are maximizing negative 10 times x1z minus 12 times x2z. So we have some other terms, but the nonlinearity appears here. So somehow we may see that if there is no limitation on x1z and x2z, say if we replace this guy by, for example, w1, replace this guy by w2, naturally if there's no restriction on w1 and w2, we will try to make w1 and w2 as small as possible so that we may maximize our objective functions. Okay, so that gives us a very quick suggestion. It says that our reformulation need to give some lower bound on w1 and w2. So let's see how to do that. Well, we still do the introduction about w1 and w2 according to the way I just mentioned. So here w1 x1z is going to be replaced by w1, x2z is going to be replaced by w2, and for this some kind of minimization objective function, we should have a lower bound. So let's try to play this trick. We're going to say w1 is going to be greater than or equal to x1 minus 8 times 1 minus z, and the w2 pretty much the same thing. So let's take x1 as w1 as an example to see how this works. So we know w1 is lower bounded by the formulation we just provided to you. Let's say z is 1. Suppose z is 1, then in this case we can see that our w1 must be greater than or equal to x1. So that somehow means as long as you make some production plan, as long as you run your production process for a few hours, you need to pay that cost accordingly, as long as you accept that order. Okay, so that's one thing. On the other hand, if we say z is 0, then that constraint should somehow disappear so that we don't need to pay anything in the new formulation. So if z is greater than or equal to, if z is 0, then our formulation, our constraint on w1 would become w1 greater than or equal to x1 minus 8. Okay, so this seems to be a constraint, but actually if you take a look at the original formulation, immediately you will see that your x1 has no reason to be greater than or equal to 8. Alright, why is that? Because as long as you set your x1 to be 8, it is enough to satisfy everything, right? So there's really no reason for you to run this production process to be more than 8 hours in some sense. So if x is actually less than or equal to 8, then very quickly you know the right hand side here is a negative term or non-positive term. So if you also have w1 greater than or equal to 0, then in effect this particular constraint is disappeared. Alright, so that somehow tells us why we choose 8 to be the coefficient here. because after the analysis on the original formulation, we know x1 is upper bounded by 8. So that's why we set 8 to be the coefficient here. If you have no other ideas, you may set this 8 to be a very large number, but of course, if you have a precise estimation, that would be better. So we play the same trick on W2, then eventually we will have a new formulation which is linear and which may still represent the original situation. So now the remaining two situations is for the product term to appear at the constraint. And suppose the product term appears at a larger side, then this will be a situation like this. So our x1z in this particular example is greater than or equal to something. So suppose that's the case, again, we try to linearize it by doing the replacement. So let's say w equals x1z. So in this case, w would need some kind of upper bound. Otherwise, the formulation does not make sense. So now you need to give w an upper bound just in a very familiar way. So in this case, your w is less than or equal to x1, and the w is less than or equal to 10z. What does that mean? So if your z, in this particular case, if your z is 0, then somehow that means your w should be 0, right? Because w is x1 times z. So your w would be less than or equal to 0, and that allows you to result in a 0 for your w. If your z is 1, on the other hand, then in that case, you are going to require yourself w to be equal to x1. Then in this case, because your z is 1, so in some sense, you're going to remove the second constraint. Why is that? Because according to the original formulation, you know there's no way for your x1 to be greater than 10. So somehow that means if your x1 can no longer be greater than 10, then in this case, once you set your z to be 1, then this second constraint in some sense disappears. It's not effective at all. So then we're going to have only the first constraint, which says w cannot be greater than x1. And that somehow requires us or allows us to set w to be equal to x1. Okay, that's how we do this. Lastly is a case where our product term appears at the smaller side of a constraint, like this. Okay, so again, we want to replace that x1z by w. So our z is binary. So again, we apply the same trick, saying that our w should be greater than or equal to x1 minus 10 times 1 minus z. We would also add another constraint, saying that w is greater than or equal to 0. Naturally, it's because our x1 is non-negative. So let's take a look at how this works. So your z may be, for example, 1. In this case, our constraint here is going to be w is greater than or equal to x1. Okay, so if w is required to be greater than or equal to x1, then according to this formulation, you're going to set w to be as small as possible. And that's going to be in effective w equals x1. Okay, so that allows us to set w to be equal to x1 as long as our z is 1. So that's one thing. Also, it's also possible that our z is actually 0. So if our z is 0, this constraint becomes w greater than or equal to x1 minus 10. So according to the original formulation, we know our x1 cannot be greater than 10. That's why we have 10 in the new formulation. If our x1 cannot be greater than 10, then the right-hand side here, x1 minus 10, is going to be non-positive. Then because we have w non-negativity, so in that case, the non-negativity constraint is going to dominate this constraint. So that constraint actually disappears, and our w can be greater than or equal to 0. And to make w as small as possible, w will become 0. And again, that makes w equals to being equal to x1 times z. So that's how this constraint, this reformulation works.